everybody, it's Ms. Phoebus and I'm back with some ancient Greek mathematics. This time we're going to talk about Thales in this video. We're going to talk more about individuals and their contributions to mathematics as we go through the ancient Greek mathematicians, just because we know a little bit more about them individually. So Thales is from Miletus, so this is the Mediterranean up here in the upper part, like where you can't see the map, that's Europe. Over here is Turkey, and the Middle East. Down at the bottom, that's Africa. And inside this little inset, we have Thales, and Thales is from a place called Miletus. We're going to talk about Thales a little bit more in a minute, but we're going to talk about just kind of ancient Greek mathematics in general. So the beginning of Greek mathematics started around 6th century BC and really went through about 5th century AD, and that was like the golden age of Greek mathematics. The word mathematics comes from the Greek word mathema, meaning subject of instruction. The Greeks had a couple different ways of writing down numbers, but the one that they used the most was they used the beginning letter of the word to represent the number. So the number 4, which they called deca, they would draw a D or a delta. This is a capital delta, the triangle, and this is a lowercase delta, and that would represent the number 4. So they have several different numbers, and then they have letters that correspond with those numbers. And so because they had kind of a clumsy way of writing, they don't have a place value or anything like that, they really didn't like algebra very much. They focused in on geometry and geometric methods to solve problems that you would probably nowadays use algebra for. They found it very hard to write down equations or number problems, so they wrote in words and sentences. So they have books and books and books explaining how you would do it instead of using mathematical notation. Greek mathematicians were very interested in proving that certain mathematical ideas were true. They spent a lot of time using geometry to prove that things were always true, even though people like the Egyptians and the Babylonians already knew that they were true most of the time anyway. So we have, this is a piece of parchment, and this is in Greek letters, and this is a proof of something. I'm not sure what it is because it's an ancient document, but they would write out these proofs and then they would leave them in books, and they would create these libraries, and you would be able to go and read why it was always true, and that yes, it was always true. So back to Thales. Thales was born around 624. That's not exact, but it's somewhere in there, BC, in Miletus, Asia Minor, which is now Turkey. But he is considered a Greek mathematician because in those days that was part of ancient Greece. He died in approximately 574 BC. He started off as an engineer, but later became one of the first of the 7 sages, or the wise men of ancient Greece. He's known as the first Greek philosopher, mathematician, and scientist. He founded the geometry of lines, so he's given credit for introducing abstract geometry. So this is just geometry of lines. And so he created some proofs, some propositions, basically, that are attributed to him. So he came up with and described and proved that a circle, when it's cut through any diameter, so a diameter is a line that goes from edge to edge of the circle and it goes through the center. So when a circle is cut by a diameter, it's cut into 2 equal pieces, it's bisected. So that was a proof that Thales introduced or explained. Another one was that the base angles of any isosceles triangle are equal. So if I know that the 2 sides are congruent in an isosceles triangle, then the angles across from them are congruent. He proved that to be true. He also proved that the angle between 2 intersecting straight lines is equal. So we have what we call these congruent angles, these vertical angle pairs. So the blue ones are congruent and the red ones are congruent when the lines make an X. He also proved that two triangles are congruent if they have two angles in the included side equal to each other, and they are that's considered to be side angle side congruency. He proved that to be true. And then he also proved that an angle in a semicircle is a right angle. And this is actually Thales' proof that he's best known for, because the other ones are kind of like, okay, I can get that. But this one is pretty deep, pretty interesting. So there is another video that I want you to watch about the Thales theorem, about the angle in a circle. And it's the guy that does, hey, Esau's, this is Michael here. And it's kind of a silly video, but it's interesting. I liked it. I thought it was fun. All right, so Thales, in the ancient Greek times, like, everybody decided that they were going to start their own school. So Thales has a school. He is the founder of the Ionian School of Philosophy in Miletus, and he becomes the teacher of a guy called Anaximander. It's been a while since I've said that name. Anaximander, who ends up being, and you don't know his name probably, one of the greatest scientific minds of his time. So we're going to talk about Anaximander later. But Thales is one of Anaximander's teachers, and he influences him quite a bit. Thales is acknowledged by a number of sources as one of the people who defined the constellation Ursa Minor and used it for navigation. Some people believe that he wrote a book on navigation, but we've never been able to find it. He predicted an eclipse on May 28th, 585. It's the earliest recorded event prior to its occurrence. But we do know that the Mayans and some of the Mesoamerican tribes were predicting eclipses, but I don't know if they had predicted this one. He is believed to have been the first to experiment with static electricity by using a rubbed piece of amber and some cloth and creating static electricity, and who knows, probably zapping people with it. But that is attributed to him. And he is known to have a mind for business. So this is one of the stories about Thales. So one afternoon, as Thales and his friends were discussing money, coins had just recently been invented, Thales made a remark: anybody can make money if he puts his mind to it. So his friends immediately said, prove it, which makes sense, right? Because they're all about proving things. So Thales was in an awkward spot, and he had to think. He said to himself, what item is useful to everybody? So his answer was oil. Remember, he lives in Greece, Turkey. So they use a lot of olive oil for soap, for fuel for lamps, for cooking, and for softening your skin, making you look nice. So Thales decided to study oil from that process of taking it from all the way from the tree, from the olives, to the oil press. So during this investigation, the first stumbling block he found was the fact that for several seasons the trees had not been producing olives. So he really wanted to know why. And then he thought about, well, trees are influenced by weather, so he thought about weather conditions. In fact, he had to do research on weather of the past seasons, the kind favorable to the ripening of olives and the unfavorable kind. So yes, he wants to make money. He's researching about olives and olive trees, and then now he's researching weather. After that, he had to try to discover a pattern in weather conditions so that he could see what to expect in the future. From his diligent work in laying out the pattern from the past, he calculated that the favorable weather conditions were due the next season. Now he made a tour among the discouraged olive growers and bought up their olive presses. Of course, they were delighted to sell them because the presses had been useless for several seasons. Besides, in the past, a grower without a press could always borrow one from a neighbor if the need arose. But when the big crop came the following year, there were no presses to borrow and none to buy either. Thales had bought them all. So Thales cornered the oil market and made a fortune. Some say he gave the presses back afterwards because he didn't have time to go into the oil business. All right, here's another story about Thales. This one I really like. So Thales inherited a salt mine. The salt was transported from the mines by donkeys. They were weighed down with bags of salt at the deposits, and then the donkeys had to carry them all the way, these bags of salt, all the way to the market. This donkey train had a long journey in the hot sun. So Thales was surprised when one of the donkeys kept showing up cool, clean, and without any salt. He's like, "What's up, dude?" He was very puzzled as to how the donkey was released on the line, like why they let him go and let him travel, but ended up not carrying any salt. So Thales thought for a while, and using some simple deductive reasoning, finally came up with a conclusion. Thales asked himself, what sort of thing refreshes the donkey and would dissolve the salt? So what do you think that might be? The donkey had found a stream. There was a stream along the route, and Thales had to think of a way to train the donkey to stop laying down in the stream. So if this was your donkey throwing away your salt that you really, really wanted to sell and make money off of, how would you teach the donkey to stop it? Like, how would you get back at this donkey? Well, this is what Thales did. Thales figured that he would put sponges in the backpack of the donkey. Not salt, but sponges. And the sponges would absorb the water and make it heavier and therefore make the donkey tired. So on the next trip, Thales filled the saddlebags with sponges instead of salt, and the little donkey's happy habit was broken. There's another story about Thales going to Egypt to study with the priests, and when he was there, he learned of mathematical innovations and brought this knowledge back to Greece, the land of the Nile. So the legend goes, Thales amazed and frightened his guides by telling them, as if by magic, the exact height of the Great Pyramid. Naturally, Thales' visit to Egypt was not complete without a sightseeing trip to the desert at Giza to see the three pyramids and the Sphinx, half buried in the sand nearby. In 600 BC, the pyramids were already about 2,000 years old. Thales hired guides and took a Greek friend along. When they reached the mighty monuments, the guides seemed proud to boast that the Egyptian pyramids had been standing when the ancestors of the Greeks were long-haired barbarians. Thales stood for a time, admiring the most gigantic of the tombs, the Great Pyramid of Cheops, which covered more than 12 acres. He looked he looked up the great slope, rising to a peak against the cloudless Egyptian sky, and noticed how the brilliant sunlight hit directly against one face and drew a pointed shadow over the desert sands. Then he asked the celebrated question, "How high is this pyramid?" The guides were dumbfounded and got into a lengthy discussion. No sightseer had ever asked them that before. Visitors were always content with the dimensions of the pyramid's square base, 252 paces along each side. Sometimes the Greek tourists didn't believe that and had to pace it off for themselves. But this one wanted to know something more, the height. So nobody knew the height of the Great Pyramid that was there around. So perhaps long ago the builders had known, but by the present dynasty, everyone really had forgotten about it. And of course, you couldn't measure it because a rope dragged all the way up to the top, and who was going to want to risk that, would just give the length of the sloping side or the slant height. Thales wanted the actual height from the base straight up to the tippy top. So they couldn't think of any way to find the height, short of boring a hole from the top of the pyramid down to its base, and that was impossible. So while the argument went on between the Egyptians, Thales and his friend had been walking around quietly, staying close to the pyramid shadow where it was cool. Suddenly, the Greeks called to the guides. "Never mind my question," said Thales. As the guides approached, "I know the answer. The Great Pyramid at Giza rises to a height of so many paces." I'm not giving it away quite yet. Terrified, the guides flung themselves on their faces before Thales, fully convinced that he was a magician. To be sure, Thales did not get the answer by magic. He simply used an abstract rule from his new kind of geometry. Thales hadn't always known about the rule of proportion, but it was something that he observed while he had been studying in Egypt. One day, while he was waiting to discuss something with one of the Egyptian priests, he thought about the accomplishments of Egyptian geometry. In the great empty space before the temple stood a high gilded obelisk made of it made a fine shadow pole or sundial in the afternoon light. A few white-clad priests and worshippers were standing about, their shadows very distinct too. Off to one side, the vast temple, perfectly laid out so that its sides would face all 4 points of the compass. And through its colonnade, he could see a glimpse of a painting, a masterpiece of Egyptian proportion. Proportion. It ran, Thales knew, like the golden thread all through the work of the ancients. Proportion was used by the Chaldean astronomers, those are the Babylonians, in the angles of their sextants and the corresponding arcs of the travels of the distant stars. Proportion was used by Egyptian architects in designing their buildings and erecting the actual structures, but it was best shown in the vast wall paintings with which the Egyptians decorated their temples and tombs. Those vivid scenes were all painted by artists using an innate feeling of proportion. Thales had seen them at work. The Egyptian artist had a very simple means of transferring his small sketch to huge tile walls. First, he covered his sketch all over with small squares, something like modern graph paper. Then he made squares all over the wall, only large ones this time. Finally, he studied where the lines of his sketch crossed the small squares and then copied these lines onto the same relative position over the large squares. That was intuitive proportion and most practical, the Egyptians at their best. But as Thales sat there watching the shadows lengthen outside the temple, he saw something entirely different, abstract proportion. While others only saw men and structures and their shadows in the hot sunlight, Thales saw abstract right triangles as well. All these triangles were made the same way: an upright object, a pointed obelisk, or a white-clad Egyptian, a slanting sun ray that hit the top of the object, and the flat shadow that it cast on the ground. Over time, Thales noticed that the shadow's lengths changed sizes, but all of the triangles changed the same way, together. The right angle and the height of the object that made its upright or vertical side, these do not change. But the rest of the triangle changed as the sun seemed to change its position in the sky. So, at each moment, all the sun made right triangles. Sorry, I read that wrong. So at each moment, all the sun made right triangles were exactly the same shape. Not the same size, but the same shape. The right angles, the heights of the object remained unchanged. But the other two sides, the other two angles, as the sun seemed across the sky. So we have something like this. We have the height of a man, we have the shadow of a man. We have the height of a tree, we have the shadow of a tree. And what we can do is we can create a proportion. Once we create our proportion, then we can cross multiply and solve for the variable, the height we don't know. So I can take the height of the man, 5 feet, and put it over the shadow of the man. 7 feet. So this is height of the man, and this is shadow of the man. Now notice that these are about the same thing, they're about the man. Then we can make this equal to, and this is our proportion, this is equal to the height of the tree. Notice that in the numerators, we have, both of them are heights, and we don't know the height of the tree, so we'll call that x. And then this is going to be the shadow of the tree. We do know the shadow of the tree. It's 14 feet. So, some things to watch out for, because setup's important. Height and height are both on top. Shadow and shadow are both on the bottom. Man and man are both on the left. Tree and tree are both on the right. So once I have my proportions set up, then I can cross multiply to solve. So 5 times 14 is 70. 7 times x is 7x. Divide by 7. So x is 10. That means that the height of the tree is 10 feet. We have a 10-foot tree. And that's what Thales was doing with his Egyptian pyramid. He came up with. So he has the height of the pyramid, and what he's going to use is a wooden stick put into the ground, and he's going to know the height of the stick, or even himself. He could do that as well. So Thales, who already knew the distance along each side of the pyramid's base, 252 paces, was busy pacing off the length of the pyramid's shadow, which was 114 paces. He knew his own height, which was 2 paces, and he knew the pace of his shadow, because his friend measured it for him, was 3 paces. So with this information, can you calculate the height of the pyramid? The 252 paces is not important here. So we want to do something like pyramid's height, which is x, over pyramid shadow, which would be 114, equals Thales' height, which is 2, over Thales' shadow, which is 3. If you take the 114, cross multiply, 114 times 2, then divide that by 3, you get your answer, the height of the pyramid. And that's what Thales did. So he's like, oh, never mind, I figured it out. So, of course, the guides promptly spread the news of Thales' magical solution to this seemingly impossible problem. When the priests of Thoth, I guess somewhere it was written down, so they found it, they verified that 76 paces was indeed the height of the Great Pyramid, according to the old records. Popular astonishment knew no bounds. So Thales was like, he was, wow, he was a celebrity. Who figures that stuff out? The tale traveled far and wide, so far and wide that it's come down to us even after 2,500 years. And the story has even more meaning today, for the Great Pyramid was a sturdy monument to ancient practical geometry. But Thales' shadow reckoning of its height was an even more stalwart monument in the development of reasoning. Thales also did geometrical research, and using triangles, applied his understanding of geometry to calculate distances from shore of ships at sea. So distance from the shore to ships at sea. Excuse me. This is particularly important to the Greeks, whether the ships were coming in to do trade or to do battle. In a letter, Thales advised Anaximander. I have to think about it. Anaximander's student Pythagoras. So Thales has an effect on Anaximander, but also has an effect indirectly with Pythagoras, to visit Egypt in order to continue his studies in mathematics and philosophy. The two never actually met though, but he did have a pretty big influence on Pythagoras. And then Thales is known for some of his more interesting scientific theories. Scientific being in air quotes. So let me get this out of the way. Okay, so one of his theories, Aristotle stated that Thales asked what the nature of a particular object was, could show case specific characteristics. So small parts combine to form larger structures. So that gives an idea of atomic structure kind of underlying that statement. The first philosophers were trying to define the substances of which all material objects were composed of. Even today, this is what modern scientists are attempting to accomplish with nuclear physics. This is another reason why Thales was described as the first Western scientist. Thales believed that water was the first principle and that the world started from water. So he's quoted as saying, "The principle behind all things is water. For all is water, and all goes back to being water." Thales attempted to describe natural phenomenon through a rational explanation. So he tried to explain earthquakes with the help of hypothesizing that our home planet floats on water, and that earthquakes happen when the Earth is agitated by waves. I'm not too sure about that, Thales. All right, so he's got some other quotes attributed to him, and so you're going to identify with one of these quotes. You can come back to the video and read them, but you're going to write on them a little bit. Why do you think it's true? Why do you think this is important? So here are some Thales quotes. "The most difficult thing in life is to know yourself. What is quite common? Hope, because even to those who have nothing else, it is still nearby. The past is certain, the future obscure. Nothing is more active than thought, for it travels over the universe, and nothing is stronger than necessity, for all must submit to it." All right, I'll see you guys in the next video. We're going to talk about a new mathematician. Bye.